This spider didn't build this web to catch food. It built it under the influence of a process it wasn't designed to detect. A wasp larva develops on its abdomen, feeding on internal fluids and gradually altering the spider's behavior through chemical interaction. Over time, the spider leaves its colony, moves to a new location, and constructs a compact web structure that functions as a stable site for the larva's next stage. What we're looking at here isn't typical parasitism. It's a case where one organism modifies another's behavior through ongoing physiological influence. Anolosomous eximius spiders rarely leave their colonies, not because they can't move away, but because the colony itself supports their survival. These spiders build large communal webs that can stretch several meters, and within those structures, hundreds of individuals share resources, defense, and care for young. A single spider separated from that system faces much higher risk. So when researchers in Ecuador began observing individuals leaving these colonies to build small, isolated webs, it stood out as a significant shift in normal behavior. As observations continued, the pattern became more consistent. Individual spiders would separate from the group, move to isolated positions, and construct web structures that differed from the communal design. In each case, a small larva was present on the spider's abdomen. This is where the Zatipota wasp becomes part of the system. A female wasp places an egg on the spider, and once it develops, the larva feeds on the spider's hemolymph and gradually influences its behavior. As the larva grows, the spider's activity changes in ways that align with the larva's developmental needs. Cases of wasp larvae influencing spider behavior are already well documented, but most involve solitary species, and that difference is important. When a larva alters the activity of a solitary spider, it's working within a system that already operates independently. There's no collective structure to shift away from. With Anolosomous eximius, the process involves two stages: reducing the spider's tendency to remain within the colony, and then guiding its activity toward a different behavioral pattern. That makes it a sequential adjustment rather than a single change. What the spider does after leaving also points away from random movement. It doesn't drift or lose direction. It relocates to a position with stable attachment points and begins building. The structure it produces isn't a standard prey capture web or a variation of its communal design. It's a different form entirely, one that the spider doesn't typically construct under normal conditions. The timing of this transition is also consistent. It occurs after the larva has been feeding for a period, but before it reaches the stage where it forms its pupal structure. That places the spider in position at the point when the larva requires a stable environment. As researcher Samantha Strauss described, the process results in a behavioral shift where the spider performs actions outside its usual range, including leaving the colony and building a new structure. By the time the spider walks away from its colony, it isn't choosing to go. Something chemical is already running inside it, actively turning off the instinct that kept it there. So the first question you'd naturally ask is, how does a larva with no venom glands, no stinger, and no real brain pull this off with any precision at all? The easy assumption is that it's just stressing the spider out, flooding its system with something disruptive until the spider stops behaving normally. But that's not what the data shows. The spider doesn't just act confused or sluggish. It runs a specific sequence of behaviors in a specific order at exactly the moment the larva needs it to. The leading hypothesis is ecdysteroid mimicry. Ecdysteroids are the hormones that tell a spider its body is ready to molt, to shed its exoskeleton and grow. When those hormones rise naturally, the spider runs a well-worn behavioral routine. Stop hunting, find a sheltered spot, spin a reinforced protective web to hang in while it's soft and vulnerable. Researchers think the larva produces compounds that chemically mimic those same hormones, so the spider's system reads the signal and runs the routine, even though no molt is actually coming. Think of it like this. The spider's nervous system has a built-in program for molt preparation, and that program already includes isolation and construction. The larva isn't writing anything new. It's finding that existing program and triggering it at the exact moment it needs a protective structure built around itself. The spider does the work because its own biology tells it to. The social bond suppression is probably a separate layer running at the same time. Anelosomus eximius spiders stay connected to their colony partly through chemical cues, pheromone-like signals that keep each spider oriented toward the group. If the larva's compounds interfere with the spider's ability to read those cues, the pull toward the colony just fades, and the spider defaults to solitary behavior, which means building alone. Now, the larva doesn't need to understand any of this, and that's worth sitting with for a second. Natural selection did the work over a very long time. Larvae that happened to produce compounds with these effects survived because the spiders they rode on built protective structures instead of wandering around exposed. Larvae that produced the wrong signals died inside spiders that kept hunting. Generation after generation, the chemistry got tighter. The full biochemical pathway hasn't been confirmed yet. Researchers proposed the EC-dysteroid mimicry model based on how closely the parasitized spider's behavior matches a spider genuinely preparing to molt, but direct chemical proof is still being worked out. The behavioral evidence is consistent enough, though, across enough observed cases, that coincidence doesn't really hold up as an explanation. There's also evidence the larva shifts its chemical output as it develops. Early on, the spider behaves relatively normally. The isolation and construction phase kicks in later, timed to when the larva actually needs the cocoon web ready. The larva's chemistry changes as it grows, and the spider's behavior changes with it. The cocoon web isn't a web in any sense you'd normally recognize. It doesn't catch prey. It isn't wide or sticky or positioned to intercept anything flying past. It's small, dense, reinforced, and built around a single central anchor point where the spider sits completely still. A standard orb web is an active trap. The cocoon web is a bunker, and the spider builds it with the same care and precision it would use for its own survival. Researchers studying a related case in Japan, where the wasp Reclinovelus nielseni parasitizes the spider Cyclosa argentioalba, found that the cocoon web shares specific features with the resting web a spider normally builds before molting. That resting web has no sticky spiral thread because the spider isn't trying to catch anything. It's a protective structure built for a moment when the spider is soft, slow, and vulnerable. The cocoon web the parasitized spider produces matches that same basic design. Non-sticky, reinforced, built to hold rather than trap. But it goes further than the basic structure. The cocoon web also includes small fibrous tufts that reflect UV light, the same decorations found in the spider's normal resting web. Birds can see UV light, and those tufts likely break up the web's visual outline for anything that might otherwise crash into it or pick at it. For the spider, they protect it during molting. For the larva pupating inside the finished structure, they do exactly the same job, deflecting attention from a developing wasp that can't move or defend itself. The spider builds in the finishing details, not just the basic frame. Some parasitized spiders modify an existing web rather than starting fresh. Others abandon their current web entirely and build the cocoon web from scratch at a new location. Either way, the end product is consistent: a reinforced, decorated, structurally sound enclosure with solid anchor geometry. Researchers think whether the spider modifies or rebuilds depends on where it is in its own building cycle when the larva's chemical signals hit peak intensity. Once the web is done, the spider moves to the center and stops. It's not dead at that point, but it doesn't move either. It just sits in the structure it built while the larva finishes feeding, then kills the spider, consumes the remaining soft tissue, and pupates inside the web. Hanging from the anchor points the spider put there. Every feature of the cocoon web maps directly onto something the larva needs. The reinforcement protects the pupa, the UV tufts deflect predators, the anchor points hold the larva's own cocoon in place. Wasp larvae don't spin webs. They don't have silk glands or the motor routines to build anything. So what the larva actually does is access a construction system it couldn't build itself, running the spider's own molting preparation sequence to produce a custom incubation chamber from one of the strongest materials by weight found in nature. What we're looking at is a parasite that ran a host's own survival system against it. The spider's molting routine, its silk glands, its construction instincts, none of those evolved to help a wasp, but they're predictable enough that a larva producing the right chemical signal can run them like borrowed equipment. The spider builds its own grave because the signal to build a protective chamber and the signal the larva produces are, to the spider's nervous system, the same signal. Any system with predictable responses to chemical input can, in principle, get redirected by something that learns to speak its language. Researchers studying related cases across different species keep running into the same open question: how many separate evolutionary lineages independently figured out this exact strategy?